We just started the compositional functions last time. We learned that before in Math 112. We know what it means. If you have two functions, then in some circumstances you can do a composition of two functions or two mappings, but this requires the domain of a function is the codomain of another function. And then you can make a composition. So just be careful about that in order for this composition to be defined. So that's one thing. And then we have seen that the composition is associative, right? It just give you two different paths to map one element to another element. These two diagrams are the commute. We say that in algebra, and we have proved that actually. So then the other thing I think is the identity mapping. I think we define identity mapping essentially, it just map where any element to itself. So the identity map is from a set to itself. Pretty simple. And it really doesn't do anything. If you do the composition of identity mapping for any mapping, it doesn't change that map at all. The associativity of composition of mapping is important. We have seen the associative properties of addition, multiplication for numbers, and for matrices and so on. These are actually manifestations of the associativity of mapping. All right. Let's just continue with this topic of compositions, and we know we have different types of functions. We have injective functions, we have surjective functions, and we have bijections. So then we would like to know, if you do the mappings of those functions, what will happen? Is there any conclusion we can draw, in either way? And it turns out that is indeed the case. But we have to be careful when we say these properties. So suppose we have three sets A, B, and C, and F is defined from set A to set B, and the function G is defined from set B to set C. So you can see the codomain of F is the domain of G. So that means we can actually do the composition of the two mappings or the two functions. All right, that allows us to define the composition of two functions. So then we have a few conclusions here. The first two is about the composition of the two functions, and the other two are the properties of the functions f and g. What can you say about composition? And the first two is if you know some properties of the composition of two functions, what can you say about each function? Okay, so it turns out that if the composition of G and F is injective, then F is injective. Okay. If the composition G and F is surjective, then G is surjective. So just be careful about this results, you cannot say, for example, in the first case, you don't know whether G is injected or not. And in the second uh, part, you don't know whether F is subjective or not, and so on. And the third and the fourth results uh, uh, are relatively easy. You know, if F and G are both injected, and G compose F is injected. If F and G are both subjective, then G compose F is subjective. So it requires both functions to have the same property in order for the composition of them to have that property. Okay, so we can prove these things pretty straightforward, not very hard. So let's, for example, if we want to prove the first result, so the given composition of G and F injected, then we need to show F is injected. Okay. All right. So so that's the first result. I assume that G compose F, which from A to C is injected. So you can see F is from A to B, and G is from B to C, right? So if we compose G and F with F first, then it maps any element from A to B, and then from B to C. So the function of composition of G and F is from A to C. And it's given that that function is injected. We need to show that F is injectable. Okay. So so what do you do? Typically you just pick up two elements in set A in the domain, and assume the two function values are the same. Then you have to show A1 and A2 are the same. Okay, if you know F, we need to show F is injected. I'm sorry. So similarly, you just pick up A1, A2 in set A and assume that F1 equals F2 in B, and then you need to show A1 is actually equal to A2. Okay, that's the typical standard procedure to prove injective functions. Okay, remember F is from A to B. Okay. But that's pretty straightforward, because if you assume f of a1 equals f of a2, where those f of a1 and f of a2 are in B, so so if you apply G, okay, G is from B to C, so so G of f1 is equal to G of a2, because f of a1 and f of a2 are arguments for the function G, and they're the same. All right. And so by definition of composition, that means that G compose F of A1 is G compose F of A2. But what is given is that G compose F is injectable. So that means A1 is equal to A2. So then we just started from F of 1 equal to F of 2 and conclude that A1 equals A2. That means F is injectable, right? So you can do the similar thing to part 2, about the surjective. And for part 3 and part 4, you can prove either of them. Okay, so let's just look at them. Part 4. So it says if and G are surjective, then G compose F is surjective too. Okay. So that's also easy because if you pick up any element in set C and G is from B to C, then there's an element B in set B such that F is equal to C, because G is surjective, right? And for the same reason, because F is surjective, so these are given. F and G are surjective, are given. Okay. So because B is in set B, then you can find an element in A, such that the f of A equal to B, because f is surjective. So at the end, you see, you can write, C is just the G of B, which is G of FA, or G compose F of A by definition of composition. So what we have shown is that pick up any element in the set C, and you can always find the element A in set A, such that G compose F of A equal to C. And remember, this composition is defined from set A to set C. So that proves the subjectivity of the composition of G and F, or F and G. Any questions? You don't have to memorize all of these results, and they're pretty easy to prove. All right, so that's another thing about composition. The next thing we want to talk about the inverse relations. Okay, and then inverse functions. The inverse relations are pretty simple. You remember, a relation is just all the pair from one set to another. So it just includes all the pairs of elements, where the first element is from one set, and the first set, and the second element from the second set. Okay, so that's a general relation, and so it's set all the pairs. If you reverse the two coordinates in order pair, then that gives different order pairs, and we call those the set of all of those inverted pairs, the inverse relation. Okay, so inverse relation always exists. You can always find the inverse relation for any relation. You just switch the two coordinates in each order pair. All right. So for example, if we have two sets A and B, A includes 4 numbers, 1, 2, 3, 4, and B includes 5 numbers, 1, 2, 3, 4, 5. And you can define any relation from A to B. So that'd be all the pairs from 1 to 2, 2 to 2, 3 to 4, 4 to 1. Okay. So this relation has 4 other pairs. Okay. Just pick up 1, 2, 3, 4, all of them from set A, and put in the first coordinate, and then pick up 2 and 1, 4 from the second set, and put it in some other pairs in the second coordinator, and we know any set of all the pairs of that kind that have is a relation, and you don't have to include all the elements in both sets, or either sets actually. So then you just reverse the order pair, the coordinates in each order pair in this set, and then that gives you the inverse relation, and we write it as R inverse or R to the -1. And so the first order pair 1, 2 becomes 2, 1, and the second order pair 2, 2 is the same. And the third order pair becomes 4, 3. It was 4, 3, and 4, and the fourth order pair is 1, 4, and it was 4, 4, 1. So you can see, just switch the order numbers in each pair, right? And so obviously the relation will be from B to A, because now elements in B become the first coordinate, and the elements in set A become the second coordinate. All right. So then The question is, if in case R is a function, does the inverse relation or inverse is also a function? And you can see from this example that's not the case. First, the R is actually a function. For each number in set A, 1, 2, 3, 4, all of them, we just paid some numbers from B um, and the first each number in the first set A only appears once in the other pairs. So that is indeed a function. Okay, remember the definition of function. But if you look at the inverse relation, you see you have two other pairs with the same first coordinate. So that's not a function, right? It maps two different numbers in R inverse. So that's not a function. So it happens, a lot of times that the inverse relation of a function is not a function. Okay. So then the natural question is, in what circumstances do we have a function from the inverse relation? Okay. And then we can check, the reasons why it does not make a function. All right. So let's just start from function f, a general function from A to B. And obviously f is a relation, f is, a function is special type of relation. So then you can always have an inverse relation. So there are two different situations that make this inverse function not a function. Okay. First, if some elements in the set B are not mapped from A, they are not the images of any elements in set A. So that means f is not on 2, right? F is not on 2 or not surjective. Then when you do the reversed relation or inverse relation, you try to map, the elements in B to A. So, but if there are some elements in B are not coming from mapping F from A, then there's no way you can map those elements back to A, right? By the F inverse relation. So that's one case when the inverse relation is not a function. Okay, and the other case is when multiple elements in set A map to one element in B. So when F is not injective, in other words, not one-to-one, then when you reverse the numbers in the other pairs, then you can see for that element with in set B with multiple pre-images, then when you reverse the order, and then that element in B becomes the first coordinate, and those multiple pre-images in set F for it becomes the second coordinate. So you are mapping one element in B into multiple elements in set A. So that also is not a function, right? You cannot map one element from the domain to multiple elements in the codomain. So so you can see when F is not surjective or F is not injective, then the inverse of F will not be functional, although F itself is function. So that automatically says that in order for the inverse relation of a function to be a function, the original function has to be bijection. All right. So this is a theme for on the next page. So that's why we require, a function to be one-to-one correspondence or bijection in order for it to have a inverse function. All right. We learned that before, but we didn't know the reason why. So here tells you the reason why. If you understand the functions in terms of order pairs again. So this is the theorem, it says let f be a function from A to B and let G be the inverse relation to F. Then G is a function from B to A, and only if F is bijection. Okay, yeah, that's what we just discussed, and it's pretty easy to prove, So so F is a function, and G we can write F inverse be the inverse relation of F. Okay. So then we just prove in two ways. So first, let's assume that F is a bijection. Then we need to show that its inverse relation is a function. Okay. So then what it means by bijection, it means every element of B is the second coordinate of exactly one the pair in F. Okay. So it is on two. So that means that tells every element of B has a pre-image in A and is also one-to-one. So that means is the second coordinate of exactly one order pair. So it does not appear any element in B does not appear twice or more in order pairs. So if you just reverse the order of the order pairs, then exactly it says is every element of B is the first coordinate of exactly one order pair in G, because these are the properties of the order pairs, right? And what they do is just reverse the order. So then that makes G the function. All right. So that's one way, and the other way, then we need to show. Suppose this G, the inverse relation of F is a function, then we need to show that F is bijection. Okay. Again, it's not hard to so because G is a function, so that B is the domain and A is the codomain. It's fun. G's function means that every element of B has exactly one order pair. It's the first coordinate of exactly one order pair in G. Okay, so then that means every element of B is the second coordinate of exactly one order pair in F, because again, G and F are just reversed order of numbers in order pairs, and we know that multiple elements of B mapping to a single element in A will not happen, because that will make the function F from A to B not a function. Okay. So then we can conclude that every element of B is the second coordinate exactly one other pair in F. It cannot be multiple order pairs in F. Okay, so then F is bijection, right? Yeah. That's the definition. Every element of B is the second coordinate of exactly one order pair in F. I think this is not very hard to understand. Any questions about this theorem or proof? No. Let's just look at some simple examples of inverse relations and inverse functions. So let's assume F from R to R be a function given by f(x) equal to x plus 1. And we have shown that this is a bijection, and it's pretty easy to show anyway. So if we write this function as all the pairs of x, y, so for any x, just compute y using this formula 2x plus 1. So the inverse relation is just flip these two numbers, x and y, so you get all the pairs y and x. And this time, you have to choose y as the variable because that's the first coordinate. So then you have to, express x in terms of y. If you do that, if you solve for this equation y equal to 2x plus 1, then you get the x equal to y minus 1 over 2, and that's pretty easy to solve. And so x just equal to y minus 1 over 2 in this set, given any y. So you can see f inverse is a function because it's a bijection. So because f is bijection, so the inverse of f is a function also, and the function is just the f of inverse is just y minus 1 over 2. Okay, that's the inverse function. Okay. Well, the previous example actually tells us how to find the inverse function as you learned in Math 112. So suppose function f of x equal y is given by a simple rule, a simple formula. If we can solve for x in terms of y, then that gives us the rule for f inverse. Okay. For the inverse relation, actually. We don't know whether it's f is bijection or not in general. Okay. So in the previous example, as we did, that's how you found the inverse functions, right? Okay. Let's look at one more example. Let's assume f is function from R to R, the quadratic function, the parabola. If x equals x squared, then if you try to find the inverse relation for this function, you actually don't get a simple one solution. You get the two solutions, right? You get plus and minus when you take the square root. If you try to solve for y equal to x squared, then solve for x in terms of y, you get two solutions. So this inverse relation is not a function, because you get two branches. So it's not one function. Okay, two branches, or two functions. So obviously, the inverse relation is not a function. But that can also be seen from the function itself, or f itself. F equal to x squared is not the 1-to-1, right? It's not injective. It's 2-to-1. Okay. And it's also not surjective, so that's the other thing, We define f from R to R. It is not surjective because the negative numbers in the codomain do not have free images in the domain under this function of mapping. So you can view this in different ways. It's not a bijection, so the inverse relation will not be a function. But if you try to solve it, you can also see you do not get just one function or one root. Okay, we all know that. Anyway, so this is not the example we did before, f(x) equals x minus 1 over x2, and we have shown that this function is a bijection. Okay, if you remember what we did before, it's from R minus set to R minus set 1. Remember the domain, the codomain or range in this case, actually. All right. So this is also important. When you try to define a function, you have to specify the domain and codomain. If those are not properly specified, then you do not get a bijection. All right, then you cannot talk about the inverse functions. Although it looks like it will be, it's actually not. Okay, so in this case, it is indeed a bijection given the appropriate domain, the codomain. And you can easily find the inverse function for this function by switch x and y, or just solve for y from ax. So x in terms of y, I'm sorry. So you write y equal to x minus 1 over x minus 2, and multiply x minus 2 on both sides, and then on the right you just multiply y with x minus 2. If you distribute, you get the x times y minus 2y, and then you move all the terms of x on one side and the other terms on that side, and group them. So then you get the xy minus x equals 2y minus 1 if you switch 2y and the 1, actually. 2y and x on the other side. And then on the left you have x in common that can be factored out. So you get x times y minus 2. On the left, then you can divide by that on both sides. So you get x equal to 2y minus 1 or over y minus 1. So that's the inverse function. Okay. So the f inverse of y equal to 2y minus 1 over y minus 1. Another thing about the notation here, also we wrote f of inverse y as function of y to denote that's the inverse function. But usually, we use the x as the variable. So usually we write the f inverse x equal to x minus 1 over x minus 1. But that should be understood in terms of y, not x. Okay. Okay, so the last thing about this section is composition of inverse functions. So we talk about the composition functions and we talk about the inverse functions, then we can combine them and see what properties they will keep if you have inverse functions and composition of functions. All right, so this f inverse notation, although you can write it for a general relation. Okay, for any function, you can write f inverse for any function f, although it may not be a function, but usually when you write f inverse, that indicates it is a function. Okay, although sometimes we do have some exceptions. So let's just assume f to be a bijection in here, and then let's see what happens for the composition and inverse functions. So f is from a function from a to b and is bijection. Then you can easily show these four properties pretty straight. The inverse of f is just f itself. That's probably one. Probably two. F inverse is from B to A, of course. There's also bijection if f is bijection. Okay. And f inverse composed with f gives you identity from A to A. Okay. Remember, f is from A to B. Okay. And f composed with f inverse is also identity function, but it's from B to B because f inverse is from B to A. And these properties are very easy to prove. Let's just prove them. Okay. First, this equality, this result F inverse to the inverse is F itself. Actually, it's true for any relation. Even when F is not a function, because when you do the inverse relation, you just change the switch the order of the numbers. So if you switch twice, then you return to the original order in order place. So that's just F. So you really don't need to prove anything in this case. So the second result says F inverse is also a bijection. If F is a bijection, that's also easy to prove. If you use the theorem we did before, because F is bijection, so F inverse is a function also. So the inverse of F inverse is also a function. All right. Because it's just the F. If you use the first part, the inverse to the inverse is F, and F is a function. So then you just use the theorem again, then you can conclude the F inverse is a bijection because the theorem says the inverse of function is a function if and only if the function is a bijection. Okay, so we know this the inverse of F inverse is a function which is F. So then using this theorem that we know F inverse is bijection. All right. The third and the fourth property are pretty easy, so just make sure you got the right domain and the codomain. F inverse compose F is from A to A because F is from A to A. So then F is from A to B, and then you do the F inverse, so that from B to A back. So F inverse compose F from A to A. So that's the same domain and codomain of IDA, right? Identity function is from one set to itself. In this case, set is A. We need to show F inverse compose F is just the identity function on set A. And so if you pick up any element in set A, then the order pair of F, A will be in F, and you switch the order, you got F inverse. So F of A is in F inverse. So that means F inverse of FA equal to A, right? So F of A is just the argument of the F inverse. And the function value is A, so F inverse of FA equal to A. So if you write in the notation for composition, that means F inverse compose F of A equal to A. So that's just the definition of composition. And so that automatically tells you that this F inverse compose F is the identity function on A, right? And A, the element A is arbitrary in set A. So we prove the F inverse compose F is identity function on A, and similarly, you can prove the fourth part, which is F compose with F inverse is from B to B is equal to IDB, identity function B to B. So that's the end of this section. Where we finished it today. Any questions about this section?